This is Timothy Wood with Citadel Civil Engineering. This is CIVL 202 Statics, and in this lecture we're going to actually introduce statics. Yay, nothing moves. So we're going to start by talking about a general overview of the concurrent equations of equilibrium and how those work. So the first thing we want to talk about is the concurrent part. So when we think about our concurrent equations of equilibrium, this is going to apply to concurrent forces. Maybe you'll need to go back and check your notes, but the key to concurrent forces is that they all their line of actions pass through a common point. So we might have a collection of forces pulling or pushing, but when we think about those forces, their lines of action all pass through that common point. Now, what that means for our concurrent forces is that we can, if we have an object, we can model that object as a particle, which meant that we were going to keep up with its mass, but not its shape. We're going to be modeling this mass at a point. So if I wanted to take an object, so just as a random example, consider maybe I have a mug like this, my Texas mug. I take my mug and I want to draw a picture of it, and I'm going to model it as a mathematical point. So when you do this, you get your fancy French mode going, you get your marker out, you hold it out, you make sure your pinky is up, and you say, there's my picture. You're going to hang it in the Louvre. But we're engineers, so this is not open to interpretation. So we want to be clear, and we might label it like so. So we're going to have a particle with a mass at a point, and then we're going to think through all of our forces. This is our concurrent equations of equilibrium. All of our forces are in equilibrium. Equilibrium, which means that we can use Newton's first law, where we're going to say the sum of the forces is equal to 0. Yay, nothing moves. All right, so here's the deal. This is our equation of equilibrium for concurrent forces. All we need is Newton's first law. The sum of the forces are equal to 0. This is a vector summation, so think of our resultant force work that we've done. But now what we're saying is that when we look at the whole system, all those forces are going to add up to 0, meaning that it's not accelerating and nothing moves. Now, instead of writing equations of equilibrium every time, we will abbreviate this to EOE, equations of equilibrium, and we're going to be so excited because we're finally doing statics and nothing moves. It's fantastic. So when we tackle a problem like this, we're going to follow a straightforward procedure. This procedure is going to be common throughout your engineering mechanics life. So it's a basic 3-step procedure. The very first step is going to be to draw a picture. So we're going to generate a sketch of a free body diagram, or an FBD. So hopefully you remember doing free body diagrams in physics. If not, we're going to cover them here. So it's okay, no worries there. But we're going to draw this picture that represents our mental model that has whatever object we've got drawn as a point where we're keeping track of its mass. We're going to draw all the forces on it. And from that, we're going to use that picture to write our equations of equilibrium. So we're going to write out all the forces and set them equal to 0. So we're going to then write our equations of equilibrium. Once we have those equations of equilibrium in place, we'll have a systems of equations, and so our last step will be to solve for our unknowns in that systems of equations. So you're going to need your systems of equation solving. Typically, I like to use substitution, but if you really want to use a matrix method or elimination, go for it. Just make sure you know how to do that. This is going to be the biggest step for many of you in terms of getting that tool back into play in your working memory. So this is our step for concurrent equations of equilibrium.